All right, let's continue with populations and demography. So continuing on, there are some terms that show up in with respect to looking at the next thing, which is growth models. And so I wanted to go over those terms with you. First of all, growth rate we've already seen. I've already defined that on an earlier slide. So let's look at the factors that are going to impact growth. And the first of these is carrying capacity. It's just what it sounds like. A capacity is how much something can hold, right? So the carrying capacity is the amount of individuals that an environment can support. It's abbreviated K, and I'm not sure why it's abbreviated K instead of C, but it is. So carrying capacity, if you see the capital letter K, that's what that means. It's carrying capacity. This is determined by something called limiting factors. So limiting factors are the factors that are usually in short supply in an ecosystem, or they're factors that are going to somehow put limits on how big a population can get. And there are two types of limiting factors, the density independent and density dependent limiting factors. So the density dependent factors are going to be things that are going to impact populations most when they're closest to carrying capacity. In other words, when a population's crowded, diseases spread faster. Lack of food becomes a real problem. Lack of space, habitat, stuff like that. Those are density dependent factors, so they're going to impact the population because the population's crowded. Density independent factors happen regardless of how big the population is. So regardless of what the population density is, these things are just going to happen. These typically fall into the category of natural disasters like droughts, hurricanes, forest fires, stuff like that. Hurricane Katrina didn't hit New Orleans because it was crowded. It hit New Orleans because that's where it hit. Those things happen, and it doesn't happen as a result of crowding. It just happens because that's the way it happens in nature. So those are things that are going to impact the population size. You also have this one thing here. You can get, if a population is small and something happens and you get a natural disaster, something like a forest fire that wipes through and kills a lot of individuals, what happens is the population size decreases so much that its gene pool actually decreases a lot. And what happens is you get increasing inbreeding, which means you get a lot of genetic disorders that pop up in those populations, and so those populations are unstable. You can kind of think of it like, if you had a population of 10 individuals and 5 are wiped out, then 50% of your population's gone. If, however, you have a population of 105 are wiped out, then you've only lost 5%. So the bigger the population, the more stable it is in general. All right, the next topic here is age structure, and age structure is a graph. It's a bar graph, and what I want you to notice is that essentially you've got gender and you've got age data on these graphs. And this is important because demographers look at this to see what's happening in populations, and there are 3 different age structures here, okay? And you're building an age structure graph in your lab. First of all, you'll notice the axis is in the middle of this graph, and you usually have males on one side, females on the other. You can see the color coding here. And then these are the age brackets. Okay, so these age brackets are going in 5-year increments. Sometimes it's in 10-year increments or whatever. These are 3 typical age structures that you would see. Okay. I'm not sure what year this was taken, but if you look at this first age structure graph, notice you've got very few individuals up top and you've got a lot of individuals at the bottom of the graph, okay? In this situation, what you have to understand is that demographers are very concerned with an age range from about here to maybe here, okay? This little age bracket right here is reproductive age. So right in here, that's reproductive ages, right? And what demographers are looking at is this part of the population compared to the part beneath it, okay? So if you look in this graph, you have low numbers relatively of individuals at reproductive age, but look at how they're out reproducing themselves. They're what we're calling above replacement. And replacement is a concept in demography where basically if a population's in replacement, each couple has two kids, right? So that means they're leaving two people in the next generation to replace them when they die, is how I think of it. That's replacement. So this population appears to be above replacement, meaning that people tend to be having more than two kids per couple, okay? And that's why this is a population in rapid growth, okay? And much of sub-Saharan Africa looks like this. I think Mexico's age graph also looks like this. What you're seeing here then is you've got a lot of people having a lot of kids. If you look at the United States, the U.S. has more of a straight up and down appearance, and you'll even notice there's even a little bit of a decline here. This is slow or no growth. Basically, this is a population that's darn close to replacement, where you've got basically couples having two kids, basically, and they're replacing themselves in the next generation. The last stereotypical type is a decline in growth. And what you see here is notice how they're not having as many kids. This is below replacement. This is what you see in Germany and also Japan. So these are some stereotypical graphs. All right, we'll come back to age structure again at the very end, but what I want to talk about now is population growth models. The first model is exponential growth, and you'll notice we are going to skip, your notes talk about the linear model, but we're going to skip it altogether. It's not important, and it's not something that you're going to be tested on. So we're going to start with the exponential model, and the exponential model says that basically over time, growth is going to start out really slowly, and then it's going to start to speed up, speed up, speed up, and then grow exponentially. So you have a slow growth phase here, and then you have this exponential phase here. Okay, slow growth, exponential growth. Now, this is a model. In other words, it's a mathematical prediction of how the population is going to grow, and every model is based on assumptions. And in this case, this assumes limitless growth. Okay, it's going to assume that growth here is limitless. Now, we know that's not true. There's always a situation where the environment is going to put a limit on the growth. You're going to run out of food, you're going to run out of habitat, there might be diseases that go through. All those density-dependent and density-independent factors that limit population size and determine carrying capacity. So this model is okay, but it doesn't take into account that something is eventually going to have to stop, put the brakes on population growth. Okay, so we need a new model. The next model, and the one that most scientists use then, is called logistic growth because it's more logical. And the reason why it's more logical is because you're automatically starting out to assume that carrying capacity is there. There is some limit, there's some end point, some ceiling. Population can't get above this particular point, carrying capacity. In logistic growth, you start the same way with slow growth and an exponential phase right here. Okay, we know that this does happen in nature. We know that in populations start out growing slowly and then they go through exponential growth. Okay, then what the logistic model says is that populations are going to slow their growth down when they get close to carrying capacity and eventually level out at carrying capacity. So the population will never get bigger than carrying capacity. It seems pretty reasonable, right? But of course, it's still a mathematical model, which means there are still assumptions built into it. And the first assumption here is that carrying capacity is constant. Now, again, environments are always changing, right? I mean, think about carrying capacity of an area before and after a forest fire. Obviously, carrying capacity is going to be greatly reduced by that event, by that forest fire. So one of the problems here is that carrying capacity is not a fixed point. It's a moving target. It'll move up and down depending on what happens in the environment. The second assumption built in is that organisms, the value of carrying capacity, we know what that number is, and that we'll act accordingly. And not only is that we humans, but any population, right? These are population rules that are supposed to apply to any population. So if you can imagine all the deer getting together, for example, and having a deer meeting and saying, okay, guys, look, our carrying capacity is 100, we're at 98, we're going to all stop mating and stop reproducing until somebody dies, and then once we get to a critical number of around 90, then we're going to start reproducing again so we don't ever go above carrying capacity. That's just ridiculous, right? It just doesn't happen. And if deer can't do that, can you imagine, trees doing that, algae doing that? Certainly not, right? So first of all, you have to know what the value of carrying capacity is, and that you have to act accordingly. Okay, so we adjust mating behavior to stay below carrying capacity. So those things don't happen. If you ask 50 different scientists what carrying capacity of the planet is, for example, you'll get 50 different answers. And that's because people take into account different things, and certain things they think are more important than others, but other scientists have different opinions about that. And so a carrying capacity calculation is really, really difficult to pin down. Okay, so all this is well and good. But again, we've been dealing with mathematical models, and mathematical models are only as good as their weakest assumptions, right? So what you need to understand is none of these models actually work in reality. Okay, so here's what happens in reality. First of all, I'm going to go ahead and plot carrying capacity on our graph. So again, same kind of set of axes. We're looking at number of individuals over time. So here's our carrying capacity, right? That's our fixed point. And for now, let's just assume the carrying capacity is going to stay stable, okay? But what actually happens is you start with a slow growth phase and you get an exponential phase, and the population really grows and it shoots way up above carrying capacity. But at this point, density dependent factors start to kick in and drop the population dramatically. Here, the population is below carrying capacity again, and so it's going to increase. And then it's going to decrease again. And notice it increases and decreases less and less dramatically each time until it levels out at carrying capacity. Because carrying capacity can't be calculated, the way that populations find carrying capacity is by oscillating, in other words, moving up and down, above and below carrying capacity, and leveling out at carrying capacity. If the carrying capacity changes, then the population goes back through this process again until it refines carrying capacity. So those models are all well and good, but they actually don't even really explain what happens in reality. 28. All right, this is important because for a long time the world's population was 1 billion people for hundreds and hundreds of years, and then in the last 200 years our population has swelled to 7 billion people, and it continues to grow. And the thing is, the majority of the population is in places like Nigeria that are what we call developing countries, where you have some issues like access to food, access to clean water, access to good health care. And that means the majority of people on the planet are in areas where some real health issues and some real density-dependent factors can kick in and really cause problems. That's the story in a lot of countries, and that's what's contributing to our overpopulation. However, there's a second problem, and that's the problem of countries like Germany and Japan that are in danger of underpopulation. Those countries are going to have issues with their economies. They're going to run out of people to fill important jobs in the workplace, and that's going to cause them to decline as well. What countries try to do is go through demographic transition. Okay, that's where you have high birth rate and death rate, like in Nigeria, to low birth rate and low death rate, like in the United States. The key is to stay here and not progress to this point where your birth rate really drops. It's difficult, but an important problem.